Now, I was a little taken aback in class that nobody remembered the definition that we're using for the potential energy, which is simply that we don't define potential energy, we define change in potential energy, and then potential energy can be defined in terms of the change in potential energy relative to any point you might want to choose. Okay, well, change in potential energy is what? It's equal and opposite to the work done by the conservative force. So that would be equal to the negative integral of the dot product of the conservative force with the displacement. And we'd better put a subscript to indicate that this is a conservative force. Okay, so that's our definition. And I really recommend that definition to you. It's one single unifying definition. And if you think of change in potential energy this way, it makes a lot of sense in a lot of situations. It can be somewhat confusing, and it prevents you from having to always reach for a formula you don't really understand. It really gives you the source of whatever the formula might be, whether you can actually do the integral or not. And again, a really important conceptual idea of what potential energy means. Okay, so a few pictures over here related to this integral, because this is ultimately a line integral in the general case. And we don't do line integrals in this course, but it's important to maybe understand the concept of a line integral. Again, so we can better understand the various formulas for potential energy, as well as the way things actually behave, the way forces and displacements actually combine. Now let's just use gravitational force as an example. If I take a mass, let's take something with mass, and move it from here to here, well, move it straight up. I'm not getting straight up very well, but if I move it straight up, then it's obvious that the force of gravity and the displacement are in opposite directions, so that we can simply use plus and minus signs to indicate the displacement and the gravitational force. And if the signs are the same, that means that we're moving in the direction of the gravitational force, and gravity's doing positive work. If the signs are opposite, then we're moving in the direction opposite the gravitational force, and gravity's doing negative work. Now, what happens if I take something here and move it up to here? I didn't move it straight up or straight down. How do I calculate the work done by the conservative gravitational force in that case? Well, let's just draw a couple of vectors. One vector representing the gravitational force, another representing the displacement. Gravitational force being constant, we don't have to do an integral. All we have to do is a dot product. We do the dot product of the gravitational force with the displacement. Now, what does it mean to do the dot product? It's important to understand that. Okay? When you do the dot product, you are essentially multiplying, and I use that a little loosely because we have plus and minus signs involved, but you're effectively multiplying the projection of one vector onto the other by that other vector. So we can think of multiplying the gravitational force by the displacement in this way. We project the gravitational force onto the line of the displacement. We get this projection vector, which we then effectively multiply by the delta S. Now we still would do the dot product of the projection. I say projection vector and I don't have an arrow over it. The projection vector would still be dotted with the delta S vector, but they're both along the same line, so the magnitude of the product is just going to be the magnitude of this projection of the gravitational force times the magnitude of the displacement. And since the projection vector is in the direction opposite the displacement, in this particular picture, the gravitational force is going to be doing negative work, meaning what? Meaning the potential energy is going to increase as you go from here to here. Because gravity does negative work, change in potential energy is equal and opposite to the work done by that conservative force. Okay? And this could be very useful in the case of an incline. If you have something rolling up an incline with this displacement, gravity's in this direction, this projection is just the component of the gravitational force in the direction of your displacement. Now, we can do that with an X and a Y, and if necessary, a Z axis, but it's not necessary to understand what's going on between the force and the displacement. The XY axes and all that are just a convenience, so you want to step a little bit beyond that in your thinking. You want to just be able to visualize the gravitational force vector, the displacement, and then after having visualized it and having understood what's really going on in terms of projections and so forth, you're going to parameterize it, you're going to do integrals, you're going to do whatever analysis you need to do, and you're probably going to do that within a coordinate system. You don't need a coordinate system, though, to make this picture. Now, there's another picture that would go with the same force and displacement, okay? And that's where you project the displacement vector onto the gravitational force vector. That's equally valid. You're going to get the same result. This is bigger than this, but then this is bigger than this, but then this is bigger than this, and they kind of balance out. Okay, we're going to be multiplying this by this, or doing a dot product of this with this. Okay, now the line of the gravitational force is here, so we're projecting the displacement vector onto that line in a way that you should be very familiar with. This would correspond to just the idea that this projection of the delta S vector onto the direction of the gravitational force vector is how far the object is raised. So we're raising the object this far, we're multiplying that by the gravitational force, and of course these are in opposite directions, so you get negative work done by the gravitational force. So this is just your vertical displacement. This projection is just your vertical placement, is just your vertical displacement. This projection is just the component of the gravitational force in the direction of your displacement. And either one could correspond to the motion of a weight up an incline or to the motion of any other object from this point to this point.